Okay, have everybody's attention. We're getting ready to get started. First off, I have a sign-in sheet that's floating around, and I appreciate if you could just sign in with your name and email address. And also, I want to introduce our speaker tonight. And our speaker tonight is going to be Paul Padley, and he's an associate professor of physics in astronomy at Rice University. And he's going to be here talking about cosmology on the microscopic scale, and this involves some interesting research that's going on at the LHC. So I'll turn it over to Paul.
Okay, so just to see, how many of you have your PhD in physics? How many are getting it? How many are undergrads, high school, whatever, range? Engineers? Okay. That's good. So, I think it's a really great time to be a physicist. There's so many different wonderful ideas out there. We've all seen these books that are coming out full of all these ideas like string theory, hidden extra dimensions in universes, things like that. And so there's really an abundance of interesting ideas out there. But I think it's actually an even better time to be an experimentalist. So the theorists are generating lots of fascinating ideas, but they haven't been well constrained by experiment. They're generating ideas, and there's not really been anything to test them and challenge them. So now new experiments are about to be turned on, and we're going to find some answers. And so what are the odds that all of those theorists are wrong? Somehow I don't think they'll be asked to give back the royalties on their books, but we're going to put their ideas to the test. Now I'm talking about cosmology, but in this funny context of doing it on a very small scale. So cosmology is the science of the origin and development of the universe, or it's an account or theory of the origin of the universe. And I'm going to be talking about physics being done at the LHC, which is at the smallest possible length scales ever probed. And so you might ask yourself, what has that got to do with cosmology? Well, they seem like disconnected things, but they're not. Certainly this fellow, who I think you recognize, is very interested in what we'll be doing at the LHC. This is another cosmologist. I don't know how many of you know him, but he's actually somebody who did something right. And that's studied the cosmic microwave background. That's George Smoot, who won the Nobel Prize for that with an experiment called WMAP. It was a satellite that was lifted up and is mapping the universe. And this is the map of the universe they made. And what you see here is a picture of the universe when it was 380,000 years old. And one of the lessons we get from looking at this picture is that the universe has structure to it. Well, you knew that because you're structure in the universe. The galaxies, the planets are all structure in the universe. The universe has structure. If the universe was created in a big bang, then you expect it to spread out in a big, amorphous, evenly distributed mass. And so the question arises, how is it that we then have structure forming in the universe? And the hypothesis is that the inhomogeneities you see on the large scale in the universe come about from something called inflationary Big Bang cosmology. And what that says is that there's a Big Bang, there's the creation of space and time and everything in it that happens, and then the universe expands faster than the speed of light. And what that allows to happen is that the fluctuations in the early universe that are allowed by the Heisenberg uncertainty principle get blown out onto a big scale. And so you get these fluctuations, these quantum fluctuations in the universe exploded out, and that's what seeds the structure in the universe. And there's a lot of evidence to suggest that that's a good model of what's going on. And so you have a picture of the universe where you have a quantum gravity epoch, which we really don't understand, a period where particle physics dominates, and then you have a period where atoms begin to form and the universe becomes transparent, and at that point the photons from that point of the universe escape. Okay, that happens about 380,000 light years. And those are the photons you're seeing in the cosmic microwave background. Okay? So it turns out to understand the structure of the universe, we really have to understand the fundamental particles and their interactions and what's going on so that we can understand these early epochs in the evolution of the universe. Now, there are two really big problems with doing this. These are huge problems. So let's break them down. Problem number one is the universe is made of mysterious dark stuff. Okay? In the 1930s, Fritz Zwicky was looking at clusters of galaxies. He looked at the clusters of galaxies, added up how much mass must be in those clusters of galaxies, and he said something isn't right. These clusters of galaxies shouldn't hold together if they have the amount of matter in them that I'm calculating. There must be more matter than what we're seeing in the universe. Okay? Since then, there's been a lot more evidence for this. In the 70s, people were measuring the rotational curves of spiral galaxies and said it doesn't add up. In fact, these days you can actually make maps of the dark matter in the universe. So this is something called the bullet cluster. And what you're looking at are two clusters of galaxies that have passed through each other. Okay? So there's three different images superimposed here. The light white stuff is just a regular visual image. This pinky color is a map of the plasma that they measure out there. So the gas. So there's a lot of gas in the galaxies. And you can look at spectral lines from that and identify that that's there. And that's a map of the plasma. So these clusters of galaxies have gone through each other. And the plasma has gotten tangled up with each other and got dragged down. But this blue region that you see here is a map of the mass, the matter in the clusters of galaxies. This is a gravitational map made by gravitational lensing and tells you how much matter is there. Okay, and it adds up to more than what you can see in the plasma in the galaxies, and it tells you that this dark matter passed through and the clusters went on through with the clusters of the galaxies. Okay, so it doesn't drag, it doesn't get left behind. So the universe seems to be largely made out of dark matter. It's about 23%, or dark stuff. It's about 23% dark matter, about 73% dark energy. Actually, the expansion of the universe is accelerating. And the stuff we're made out of is a small fraction of the universe. So one of the problems we have understanding the universe and the early universe is we don't know what it's made out of. Since I do experimental particle physics for a living and I'm trying to study the fundamental particles and forces of the most fundamental constituents of matter, the fact that we don't know what the universe is made out of is a little bit of a problem. Okay, there's lots of theories to explain what dark matter is. Okay, what they consistently predict is that these dark matter particles will be produced at the LHC. And we won't be able to see these dark matter particles. Okay? What we'll do is we'll have to indirectly infer their existence. There's nothing new about doing that. The electron neutrino was postulated by looking at the beta decay spectrum in the 1930s. This is the spectrum from bismuth 210. And by looking at the spectrum, you could infer that there must be more than two bodies involved in the decay, and there's something missing going off, and that was the neutrino. And it wasn't until the 50s that people made a direct observation of the neutrinos. So that's something we've done before. So the key signature for dark matter is we make something undetectable in our experiment. And the way you know you have something undetectable is we presume energy and momentum are still conserved. And so you look at the momentum in your detector of all the particles you create, and if there's a big momentum imbalance, then you say, I'm probably making a dark matter candidate. Okay. Problem number two, well, we can actually do an experiment. I'm going to take a piece of chalk. Okay, and when I take this piece of chalk and I throw it up, what happens? Somebody tells you what happens. Comes back down, right? So it goes up. From the moment it leaves in my hands, gravity's pulling down on it. Okay? So from the moment it leaves my hands, it takes all the time to get up here, being slowed down, then it gets pulled around and it comes back down. So the gravity that stops this piece of chalk from flying upwards, okay, takes several seconds to do its business. If I drop it down, it comes down, stops right away. In fact, the forces in the table that are stopping it are so strong, they shatter it into little pieces. When I threw the chalk up, gravity didn't shatter it into little pieces. When I let it drop onto the table, it shatters into little pieces. And the reason why that happens is it's the atomic molecular bonds in the table that's stopping it. And that's the electromagnetic force. Okay? So the force of gravity stopping it on the way up is 40 orders of magnitude weaker than the electromagnetic force that stopped this chalk on the way down. Right? So that's a 1 with 40 zeros after it. That's a huge difference. And basically, nobody's ever been able to mathematically, in a predictable way, overcome that. So if you look at the forces of nature, you have the weak interaction, electromagnetism, the strong interaction. These all have the same quantum mechanical structure. And then gravity comes along, and it's non-Euclidean geometry. It's totally mathematically unrelated to these forces. And there's this huge gap of 40 orders of magnitude. It's hard to come up with a theory that can span 40 orders of magnitude of validity. And so there's a real problem there in trying to incorporate gravity. So if you want to unify the forces, and most physicists agree that that's something we should be doing, and that must have been what happened in the very earliest epochs of the universe, we've got to reconcile gravity with quantum mechanics. And the fact that we haven't is telling us something. It's telling us something is incomplete in our understanding of the forces of nature. Okay, one of the ideas, and the words here in the cartoon is just for fun, one of the ideas, and it's what some of those books you've been reading about that's out there to overcome that problem, is an idea of extra dimensions. That there are curled up extra dimensions in the universe that we're not sensitive to, because we're on a big scale, but they're on a small scale. And if you play around with such theories, you can make gravity weak. Okay? So it turns out that at the LHC we're also sensitive to many of these theories that have been postulated to explain why gravity is so weak. Okay. So what have I told you so far? We have to understand the fundamental particles and forces that govern their interactions in order to understand the early universe and how the structure we have today evolved. Fortunately, we don't know what the universe is made out of, and we have an incomplete understanding of the forces, in particular gravity. I see that as an opportunity. I see that as job security. It gives me something to go out and do. Okay? The LHC is turning on. And so just changing gears a little bit, I think it's interesting that new instruments lead to new science. The Hubble Space Telescope, WMAP, when they were building the Hubble Space Telescope, they were thinking of measuring the Hubble constant, measuring other things about the universe. If you had said in the proposal to build the Hubble telescope, the most important thing we're going to do is find the accelerating expansion of the universe, the grant would have been shot down. Nobody would have believed that. Nobody was thinking of that. You build new instruments and you get new discoveries. Hopefully things that you haven't seen before. And our astrophysics, astronomy colleagues have been, getting all the interesting results lately because they've had the big new facilities not so new anymore, but they've had these big facilities come online. Now we have our new accelerator complex coming online, and so presumably we're going to get equally interesting results, and some of those will be of cosmological interest. But now I want to change gears and talk a little bit about the accelerator and the experiments. Okay, so I'm going to talk about the LHC, and then we'll connect the different parts of the talk. So there's an aerial view. In fact, what I like to do, let's see if this works. Let's try it out ahead of time. In fact, the best graphic I've seen comes from the New York Times. Loading. Okay. So here's an aerial view of Geneva is over here. The Geneva airport's right there. I have an office just over here. Okay, and this is the LHC, the Large Hadron Collider. Okay, it's 26 kilometers around. The experiment I work on is CMS. It's over there. It's on top of the frequent flyer miles I get flying to Geneva. I get lots of car rental fees driving to and from the experiment. And what we do there is accelerate two beams of protons in opposite directions, and they go around and around this ring. The two beams, protons, are timed to collide inside these detectors. This is the detector I work on. It's the compact muon solenoid. It's 12,500 tons of highly instrumented detector. Actually, this is a funny scale. I mean, that person isn't that big. It's 5 stories high. Okay? And what we're going to do is shoot the protons around. There'll be a collision. A pile of particles will come flying out. And with all the instrumentation in that detector, we're going to be able to see what's flying out, the fundamental particles that come flying out from that collision. And then we can reconstruct what happened at the point of impact by studying the kinematics of all these things flying out. And I'll show you examples of physics signals from that in a bit. So here's an end-on view of an event. Now we're looking end-on in the detector. There's been a proton-proton collision here. And what you see are all these particles flying out in various ways. And we basically have a huge array of online electronics, computers, and that looking at the patterns here, and then try to reconstruct what happens in the collision. And I can give a whole course on how that works. It's an amazing project. So it's 27 kilometers around. It's 100 meters underground. That's interesting. The vacuum in the beam pipe that carries those protons around is comparable to space. It will be 3,000 bunches of 100 billion particles in each bunch. The power of the beam is the same as the kinetic energy of a car going 1,600 kilometers an hour. If you lose control of that beam, really, really bad for your health. It's bad for the health of your detector. And there's a lot of effort to make sure that if you lose control of the beam, it's done in a controlled way. Okay, the beams go around at close to the speed of light. A beam circulating for 10 hours will sort of make it to the planet Neptune impact. That's the sort of distances involved. Okay, this is 3,000 kilometers of fiber optic. Okay, the raw event data rate coming out of just our experiment is 40 terabytes a second. We pack the detector full of all kinds of processing power in order to cope with that. I work on the compact experiment. The Atlas experiment is even bigger, but they don't weigh as much. It's sort of got more empty space in it. Here's just a blow-up view of the detector. There's a person for scale, and you can see here, in particle physics, we have so many co-authors that we had to resort to listing the institutions. Now we have so many institutions, we've taken to listing the countries. Because you can't get all the names, forget about the names of the people, you can't get the names of the institutions on the picture. And so now we just settle for listing the names of the countries that are involved. So it's a big international collaboration. Construction began in 1998. We've been working on it a long time. One of the first things they discovered is construction had to be stopped. And the reason why construction had to be stopped is they started digging, and what they found here was a Roman farm house. And it was an archaeological site. As soon as you hit something of archaeological significance, you've got to stop construction. They worked out a deal with the French government that they could retrieve all the artifacts from there and promise to put them on display, and that allowed construction to continue. So here's the construction in progress, looking from view. And what we did is we first built this big hall here, and the detector was assembled above ground in slices. And then this building was extended out, and the detector was lowered down that hole that's being built here. There's the underground cavern in an early construction phase, so the detector gets lowered from above ground down into there. There's sort of the hall as it was getting ready, but before the detector got lowered. Here's actually the bit of detector I've worked on for 10 years as it was assembled on the surface above ground. It's very photogenic. Here's various pictures of the detector being lowered down. Each one of these pieces of the detector runs about 1,500 tons. You don't go to Walmart and get a crane to do that lowering. You have special contractors come in and do it. Here's actually a movie.
That's like a small World War II destroyer.
Yep. This thing being lowered right here is a superconducting magnet. Okay? It's the largest superconducting magnet ever built in terms of stored energy. The energy stored in that magnet is equivalent to the kinetic energy of a 747 in flight.
What's the material?
It's classic superconducting wire, niobium, whatever, I forget what it is. And then it's sitting in a cryo vessel there. One of the moments of excitement that occurred when they looked to lower, if you look at the edge here, there was a few centimeters clearance on either side. So this is actually a 1,900-ton piece of detector, and it's being lowered down, and there was a few centimeters on either side of clearance. It turned out when they did the shaft, they systematically went on the inside spec of the size of the walls. And the shaft was a little bit thinner, a little bit smaller in diameter than it had been hoped for. Here's sort of towards the end, these last bits were getting lowered down. I keep showing this one because I worked on it for 10 years. It's obviously the best bit of the detector. Okay. The plan was, when we first turned on, we used funny units for measuring how many protons we have in the beam. But the take-home message is, this is sort of an early running what one would expect. I was on the Fermilab experiment, D0, that was one of the two experiments that discovered the top quark with a couple of dozen events. At the LHC, we'll be making top quark pairs at a rate of 16 million or more a year. Likewise for other fundamental particles. If the Higgs boson exists and has a mass of 120 GeV, we'll make 800,000 of those a year. Okay? So the particle production rates are huge there. That's what's really interesting about it.
Pardon me for my ignorance, but what's a gluino?
Yeah, thank you for asking that. Ask me questions along the way. It's a lot more fun. One of the theories for dark matter is something called supersymmetry. Okay? A gluino is one possible supersymmetric particle that could, in some supersymmetric theories, be produced. Okay? So the idea is, if supersymmetry is a correct idea, and supersymmetry is embedded in the idea of superstrings, and string theory, if that's a correct idea, then we'll be producing thousands and thousands of supersymmetric particles. This is just one example. One of the problems is there's a lot of free parameters in the theories, and so which particles you produce at what masses is up for grabs. And so that's just put there as an example. What that means is those theorists who wrote all those books, they should be quaking in their boots, because if they're wrong, we'll find out. There'll be a little bit more on that. Okay, so how do we look for dark matter? Things such as supersymmetry. Here is actually an example of how a supersymmetric event would look in our detector. So what we see are sprays of particles coming out. But when we look at this cross-section of the detector and add up the momentum going all the way around, what we find is there's a big missing piece of it. And the big missing piece is this big blue arrow here. So in this simulated event, and this is just a simulation of a potential supersymmetry signal, you get a pretty clear signature of missing energy. Okay, so that's what we're going to look for in the experiment. It's missing energy like that. When you first turn on the experiment, there's a problem doing it. This is a plot of such a quantity from Fermilab, from two experiments, the D0 experiment that I worked on, and the Tevatron, the CDF experiment, both at the Tevatron. And they made a plot of that, and what you see initially is all kinds of structure. And then they start taking out runs where there was something wrong with the detector, and you get this. You start taking out noisy channels, and you get that plot. And by the end, you end up with something that looks very much like would be predicted by the standard model without any mysterious dark matter candidates being produced. Likewise at the CDF experiment. And what happens is, in some sense, measuring that something's not there is much harder than measuring something is there. If I see a big particle or a spray of stuff entering into my detector, that's really easy to detect. If I want to calculate accurately how much missing energy or missing momentum was pointing in that direction, that means everything around here has to be measuring everything perfectly. If there's a bit of the detector not working over here, it'll be reflected in a momentum imbalance. Okay? And so it's going to be hard to do that in the early running because we're first going to have to measure and make sure our detector is working well. And so we'll see lots of missing energy when we first turn on the experiments, and that'll be evidence of problems with our detector. But ultimately, we'll work all those out, and then we'll start searching in earnest for the dark matter candidates. That's not going to happen in the first year or so. That's going to take a little while to happen. Okay? So we're going to get there. It'll take a couple of years. Turns out looking for extra dimensions might prove to be a lot easier. Okay? So many theories, as I said, invoke extra dimensions to explain why gravity is weak. Many theorists write books about it. Okay? So if such a theory explains the difference in strength between electromagnetism and gravity, then we should be able to find evidence for it at the LHC. And it could be pretty quickly. So one thing, there's actually an idea out there called Kaluza-Klein. And this is an idea where you extend, Kaluza and Klein tried to unify electromagnetism and gravity back in, I think, the 1930s, maybe a bit earlier, by invoking extra dimensions. So that's an old idea, but what you notice is I've made a plot here of Google Scholar hits. And what finer measure of scientific interest is there than going to Google and saying how many hits you have. And you look at Google Scholar hits as a function of year. And there's some sort of steady state of theoretical interest. And in the 80s it starts taking off. And in the 90s it just goes bananas. Okay, this running about 13 to 1,500 hits per year in Google Scholar. It's dropping off here just because I made this plot in the middle of last year, and so not all the papers were submitted. There's thousands of papers published on the idea of Kaluza-Klein particles. And so, I don't know if they're true or not, but there's a lot of theorists banking on it. And what's the idea behind a Kaluza-Klein particle? So we have to remember undergraduate quantum mechanics, right? And if you have a free particle traveling through the vacuum, you describe it with a wave packet, right? So you have a packet of waves that travel through it, and it makes a nice little pulse, and that travels through the vacuum. But also think about a particle trapped in a box in your undergraduate quantum. And if you haven't taken quantum yet, think of notes on a violin string. Okay, you get discrete notes on a violin string. Likewise, in the quantum world, you get discrete states that are allowed when you trap a particle in a box or any sort of potential well. Okay? So you get these normal modes. And in fact, the geometry of that can be quite complicated. So in chemistry, you can have a benzene ring, and there are electron orbitals where the electron's trapped to run around this ring. Okay? So there's all kinds of complicated theories of wrapped up extra dimensions. And a particle in those extra dimensions would be like an electron trapped in a benzene ring, or whatever the geometry happens to be. Okay? So one of the ideas is the universe has extra dimensions, but they're curled up in some weird geometry on a very small scale. Okay? But if a particle is traveling through our space, but also sees the extra dimensions, you're going to see its wave packet. It's going to look like a normal packet, normal particle. But you're also going to see all these normal modes, like the notes on a violin string, where it's modes that are trapped from the energy that's trapped in these extra dimensions. So if you combine the two effects, you get things like, say, this is a plot of lepton pairs, and sitting way off here, off the plot, is something called the Z boson, and it was in my initial plot, and there was, we make lots of those at the LHC. But you can make the same plot, and then you'll see bumps in the data, like that. And those would be the normal modes of the Z boson as they float through these extra dimensions. And the reason why we haven't seen them yet is because this energy scale hasn't been accessible to us before. And this is absolutely fantastic, because I can guarantee you the first thing we will do when we turn on the detector is do what's called a Drand-Yell spectrum. Well, we'll smash the protons into each other and look at lepton pairs coming out. And the reason why we do that is we know the Z boson exists. And so we'll want to make sure in our detector we can see the mass resonance. We'll see a peak in the data corresponding to that particle. Well, we're not going to cut off the plot at the Z boson. We'll look up in energy. And it could be we just start seeing extra bumps. And if we see the extra bumps, that's evidence of extra dimensions. Okay? There's various, different, there's all kinds of extra dimension theories, different.
Yeah. Oh, and in addition to the extra power that you have in the LHC compared to other existing detectors, is there also, what's the difference in sensitivity and the detect? I mean, is there significantly difference in the sensitivity of the detectors, or?
No, I mean, the two big differences is the energy. So the design is to collide 7 TeV protons onto 7 TeV protons. And so what that means is the length scale, if you remember de Broglie, right? The wavelength of a quantum mechanical wave goes like the Planck constant divided by the momentum. So if you have a much higher momentum, the length scale of your wave is much smaller. So if it's on the side, if your momentum's high enough that your length scale becomes shorter than the size of the extra dimensions, then you'll start to see effects. So just energy gets you something. The other thing that's really different at the LHC is the luminosity, the amount of proton collisions we can do. And that's important because actually a proton's made out of stuff, and there's a probability function of how energetic a collision will be. And so the more collisions you can get, the more energy reach you get. Okay? So those are the big differences. The detector itself isn't particularly more sensitive. It's just bigger because the energies of the particles are bigger. Okay? So here's what such a decay would look like. So here we've made a Kaluza-Klein resonance of a Z boson. And what you see flying out of the detector are 2 back-to-back muons, which are actually pretty easy to identify. Okay, you see stuff, but you see these tracks just whipping right through, coming out either side. And that's a very easy signature to get. This is the easiest possible thing you can do at the LHC. And then you make an invariant mass plot of those things, you calculate the kinematics of that, and if you're lucky, you come along and you see a bump like that. And I don't know about you, but I don't need a lot of statistical sophistication to be able to see there's a bump in that data. Yeah.
This Z prime is
Yeah.
something that you are combining weak interaction with gravity. Is that what happened in Columbus line?
Yeah.
And this Z is a kind of resonance which is established when the unification takes place. Not unification, it should not be quite unification, but it is just like that, then when you take one quanta which can describe both interactions. It's not in the sense of unification, it is
No.
just in the compactification sense.
Yeah.
In the So what is the scale of Z prime? That was my question.
Oh, you mean the length scale in this case?
Yeah.
You know, I think the simplest thing to do is do h bar over this number, right? Yeah. For h over that number. And that gives you an order of magnitude, whatever that comes out to be.
Yeah, it should be the energetic and it should be higher than Z because you are calling it...
It's got to be higher
Mass
than
of
the Z, or we would have found it already.
Yeah.
Okay? So, I mean, people are, been looking for these for years at the Tevatron.
Yeah, I know.
And we haven't seen them. And so the current limits are up a few hundred GeV.
Oh, okay, that's what I was trying because
Yeah.
it should be pretty different from Z.
Yeah, so the current limits are up a few hundred GeV, 500, 600, something like that.
Hopefully it's not related to Higgs.
Hopefully it's not related to Higgs. And there's various ways, but, I showed in those books, there was a book by Lisa Randall, and she's famous for a particular type of extra dimension theory that I won't get into. And you don't have to understand the axes here. What I want you to understand is that if the unification of the forces problem is solved by her theory, then we should see something in this plot in this blue region. And with half a year of data at nominal initial luminosity, we will have examined this whole region of this plot. So that tells you very quickly we can start ruling out or discovering extra dimension theories, whether they're right or not. Okay? And there's various examples of those. This is more for the specialists. But the message is there are lots of extra dimension theories that we will be sensitive to in the earliest running. It'll be one of the first things we look for. This is just a card to remind me there's actually a different class of extra dimension theories, which are called large extra dimensions. So when these guys, Akani, Hamed, Demopoulos, and Volley, wrote their paper, they realized that gravity hadn't been tested on the sub-millimeter scale. And in fact, the extra dimensions could be as large as a significant fraction of a millimeter, and nobody would have detected it at all. Well, the first thing that happened is people started redoing the Cavendish experiment and measuring gravity at tiny length scales. But these theories give you a slightly different effect in the data. If there were no extra dimensions, for example, you make that same plot of invariant mass and you see data coming down like this, and then this is various extra dimension theories. That time. So that's interesting, and these are just limits. So the message is, and somehow Einstein knew this, is the compact muon solenoid will be able to test the space-time structure of the universe by looking for the event. You think? Go there and they'll fake up pictures for you. Oh, I went too fast. Okay. So we haven't done that so far. What we've been doing in the past year is running on cosmic rays. And I'll explain why in a moment. So we have cosmic rays coming down from space. And that's a great source of data for us when we don't have beam. And you're looking at cosmic rays that came flipping through the detector that we use to measure. And we use that to calibrate, understand the detector when we don't have beam. We've looked at lots and lots of cosmic rays. Then September 10th last year, we had the greatest achievement any scientist could make, which is Google recognized us. We can stop now, go home happy. We made it to the Google webpage. And the reason why we made it to the Google webpage is they turned on the accelerator. So the accelerator turned on. It's interesting to note that people worried that we create a vortex in space-time and destroy the universe or the planet. I'm not saying anything, but some of us were mad that the SSC got canceled. Do you think it was an accident that Ike came and hit the Texas coastline shortly after that came in? Here's what the beam looked like on our detector. What was happening in the early running of the beam, there was lots of particles whipping around with it, and it hit the detector, and we got splashes, and we were starting to understand that and understand how the detector worked when there was a little problem. And the little problem that happened is these are, there are these superconducting magnets all the way around the LHC ring, and the current between the magnets is carried by something called a bus bar. Okay? These are superconducting. But at some point there had to be a splice where the bus bar from one magnet comes into contact with the bus bar from another magnet. And on one of the magnets, it appears, well, the day they were splicing it together and doing the welding, there was an emergency evacuation of the accelerator tunnel. I mean, you're working 100 meters underground. I mean, there's a lot of safety precautions you have to take. And they think when they came back down, they forgot to finish that weld. Okay? So what happened when they started ramping up this magnet, running beam around, is this weld started to fail. It hadn't been finished right. And there was some arcing that took place. Okay? This is sitting in a bath of liquid helium. Having something spark in a bath of liquid helium is really, really bad. Because liquid helium starts turning into gas. The way they describe it is there was a rapid release of helium and a pressure wave resulted. Yeah, explosion. You cannot find the word explosion on the CERN website or any of the PRs. There was a pressure wave. They dumped 6 tons of helium, okay, into the accelerator tunnel. They froze the air in the accelerator tunnel. 6 tons of helium is actually a significant impact on the world production.
Did they recover that, or?
No, that was gone. That's yep.
Isn't helium going at a premium
Yep.
these days? Isn't
It wasn't the best physical thing to do.
Right. Well, the
Yeah.
resources are dwindling.
One thing stops being a superconductor. What happens to all the energy in that magnet?
Oh, that's a great question. Yeah. So there were 200 of megajoules of energy that had to be dumped into shunt resistors. When I say resistor, you think of something this big. No, these are things sort of that big, in the length of this room. Okay, so they had thought of all that they would have things going normal, and you would have to dump all that energy. Okay, I mean it's a big problem with. I told you the stored energy in the magnet in our detector is equivalent to the kinetic energy of 747 in flight. If that magnet goes normal, you've got to dump all that energy somewhere. They test all the systems. That they got right, okay? But what happened was actually the pressure relief wasn't as good as they would have liked. And so things like this happened, okay? So there were a number of magnets that got damaged. They warmed it up. I mean, I picked this picture because it looks spectacular. Okay, it looks dramatic. But, there was, I would use the word explosion. They didn't initially tell us what was going on, but I'm sort of on the phone to their lot and all this was happening. And we knew something was up when they wouldn't let us turn on our detector because we couldn't have any fire brigade coverage because the fire brigade was so busy for a week cleaning up the mess that had occurred down there. Well, when you freeze the air, I mean, there's sort of oxygen depletion hazard problems and things. Okay, they're well on their way to fixing everything. And in fact, today's a momentous day. Today was the official announcement of the new schedule. And so the new schedule has us turning on in September 2009. The energy will be a little bit lower than design energy, just to be cautious. And what they're going around in the meantime is putting in a lot of pressure relief valves and that. That's what the time's being used for. Okay? And so the number of events you will get, yeah, they're going to also start with a much lower luminosity, not pack as many protons in the beam, all in the sake of caution. So the number of events that you get are greatly reduced. But if there's, say, a Higgs boson of 120 GeV, there'll still be 8,000 of them produced. And that's, it's not a coincidence that these are the run parameters. They've been picked because we know we can make discoveries even with that amount of data. Okay, so I'll stop here. The LHC is going to turn back on in September. It's a discovery machine. I've talked on two possible things we could discover. The dark matter candidates, whether it's supersymmetry or whatever. That'll be a bit hard to do initially, but we'll get there. Extra dimension theories, those theorists should be having difficulty sleeping because we'll be able to chase down their ideas very quickly. I'm pretty sure the most interesting things we do are stuff I haven't talked about, I haven't thought about, haven't even dreamed of. So I'll stop there. Yeah?
Do the theorists have any ideas or any notions of other types of events that are not dark matter, but would have signatures that would mimic dark matter enough that you have to worry about?
Yes. So there are neutrinos being emitted all the time. And so when I showed that plot of, say, dark matter, there's this falling spectrum, and that's the known stuff. That's the known. And the neutrinos are known to have a little bit of mass. We don't know how much. But it seems like there can't be enough mass in the neutrinos to explain the dark matter in the universe. But absolutely, the background is neutrinos. Yeah?
How sure are the theorists, and they must be sure because it's gone on for so long and so many people, but how can you explain to me, how do they know that they've calculated correctly the known, approximately the known visible matter?
Oh, in the universe?
Yeah, so, so they can come to this conclusion that, 96% of it is dark.
So it's done multiple different ways. So the easiest, simplest things you can do is you can look at galaxies like the Milky Way. The visible matter is what you can see glowing in the stars or what you can see from the spectral lines from the plasma there. And you can just add that all up. And then you can make a plot using known physics of, how do I pop the screen up? Projectors or projector? So if I make a plot, I'll do it over here, this way, the velocity of my rotational arm as a function of position out, okay? Regular kinematics will tell you it follows some distribution like this.
Might be, that might be useful.
And then what you find is it goes out like this, okay? And the only explanation for that is some sort of dark matter. People can actually make maps of the matter, the mass energy out in space by doing gravitational lensing. So you look at a point in space, and we know from relativity that light has a gravitational attraction, and you can see it bending around a mass. And so you look at light from distant galaxies, and then you see little lensed images of those galaxies around. They're very faint, but you can do it with the Hubble, and there's specialized instruments doing that. And so you can take those images and calculate how much mass was needed in order to get these little images. And again, you come up with dark matter. Okay? Look, going back to the 30s, you look at clusters of galaxies, and it just doesn't add up that they hang together without throwing the dark matter in. So there's a lot of empirical evidence that there's dark matter out there. What the dark matter is a theoretical free-for-all. Okay, there's all kinds of candidates. The Kaluza-Klein type things I mentioned are dark matter candidates. There's no shortage of ideas. Microscopic black holes. There's a long list, and we'll have to start chugging through all the possibilities at the LHC. At some level, it doesn't matter because the signature is the same in the detector of all these candidates. So we'll presumably at some point detect, or not detect, whatever the right expression is. We'll see stuff is missing, then try to study the events and provide guidance to theorists to figure out what it is. Yeah.
How long is it going to take to reduce the data you get from an experiment? I mean, is it going to take months to determine if you found something new, or will you know right away? And is that stuff going to be available? Or
So there's actually a big difference between us and the astronomy space business, which is an astronomy data is usually made available to the public. And an instrument like the Hubble's put up there, and then scientists can apply for time, get time on it, and then there's a path by which you have to make the data available. Particle physics works a little differently. Instead of paying money to contractors, other than for, say, big structural, like all the steel on our detector is done by Kawasaki, for example, it's built by university groups. So all those countries have university groups that are all contributing and building parts of the detector and bring it together. And so access to the data and authorship rights are granted if you have contributed to building and operating the detector. And that's sort of the trade-off. So I'm expected to spend 25% of my time making the detector. I actually personally spend a lot more of my time on that, but that's me, what I'm doing at this point in my life.
So I guess the real question is, how do we get in touch with you after?
So I think if there's a big discovery, it'll be on the front page of the New York Times. I think there's a range of opinion on how long it'll take to be getting the answers out. I think some of our colleagues who haven't worked at the Tevatron have maybe a more optimistic point of view than some of us who have more experience with hadron collider physics. That being said, there is this discovery potential. I mean, if there really is some Z-prime resonance that pops out in the lepton pair mass distribution, it'll be pretty quick and easy. Life probably isn't like that. Yeah.
Okay, suppose you run this thing for years and years, the Higgs never shows up, then what do you do? I mean, you do this for years, and then the Higgs never shows up, and then where do you stand in theory?
If the Higgs doesn't show up, then we're theoretically screwed. Okay? And the reason why I say that is, in fact, for a lot of the standard model processes that we've studied, in order to get the theory right, you have to bring the Higgs into the calculation. Okay? So if you try to globally reconcile all the particle physics data, then it's actually necessary that the Higgs exists to explain that data. And you can even calculate what its mass is with big error bars. Okay? So there are corrections to current measurements that involve the Higgs. So if we don't find the Higgs, then we really don't know what we're doing. And I always see that as an opportunity. Okay? The nightmare scenario is we turn on, we find the Higgs boson and nothing else. Then I don't know what you do. I mean, that's actually the nightmare scenario. We find the Higgs boson quickly, then our standard model of particle physics that explains all the forces except gravity works perfectly in all energy regimes we can conceivably access, and we haven't solved the gravity problem, and then I don't know what we do. Yeah.
There is one alternative idea besides dark matter to explain this, rotation curves and some of the other data. It's probably a minority opinion in the physics community right now, and that's modified Newtonian dynamics, where gravity starts to act differently at very low accelerations, just like it acts differently, according to Einstein, at very high gravitational intensity. What kind of signatures would you expect, if any, from this collider, if the modified Newtonian dynamics turns out to be the right answer?
Yeah, and it's even that. And the dark energy could actually just be what's called the cosmological constant and general relativity. And then it's maybe not so interesting to the particle physicist. There's a lot of reasons to believe that there are particles beyond what we found just from a purely particle physics point of view. The ideas like supersymmetry, superstrings, all these ideas that are out there to get into books were motivated not to explain dark matter in the universe. They were thought up to actually reconcile difficulties that we have in particle physics. And then people go, wow, we've got this problem, the cosmology, astrophysics community have their problem. Maybe it's the same solution for the two, okay? Without getting into it, I mean, there's a lot of reason to think the standard model of particle physics is fundamentally flawed, not least of which is the number of free parameters in the theory. So if it's a fundamental theory of nature, we have something like 40 to 50 free parameters. For example, in quantum electrodynamics, the electron is an infinitely small point particle. Okay? You can show through what I call the renormalization group equations that you can make all the infinities that arise from having that infinitely small point particle all cancel out, and you're left over with something, but you don't know what the leftover is, and you have to put it in by hand. Put it in the electron charge by hand. But the electron also carries mass. And nobody can get their heads around what it means for an infinitely small point particle to carry mass. Well, I take that as a clue that there's something going on. I mean, we don't understand the origin of mass, and we can say it's the Higgs boson. Okay? But when I invoke the Higgs boson to explain particle mass, what I'm saying is there's a coupling to the Higgs field with a certain coupling strength, and I have to put that coupling strength in by hand.
So basically, you're just putting the problem back one step.
You're putting the problem back one step, but I haven't reduced the number of constants. Okay? So I fundamentally don't know why particles have the masses they do. And the force that acts on mass is gravity, and I don't have a quantum theory of gravity, and I take that as a big clue that there's something that we have to discover. But, I could be wrong.
But has anybody thought through whether there would be any kind of signature that you'd see in this collider if you had a modified notation?
They may have, and I haven't, and I don't know about it. Okay, I have to confess, I've been worrying more about Wiener power supplies and plumbing and
I just wondered.
flow restrictors and things like that. And I get to give a talk like this now and then and think about something other than power supplies. Yeah.
You showed a chart where you were talking about different number of events. And I just noticed that you mentioned that BB bar events are much bigger than everything else. I can expect with Higgs, but I was not expecting with...
Because the B quark is so light compared to everything else.
Sorry?
The B quark is so light compared to everything else that we just make it in vast, huge quantities.
No, I was just interested to know that what kind of model they are using. I mean, it is SUSY, I suppose.
To get the B quark production?
No.
Oh,
In general, that they...
all these rates. Oh, right. You turned that off.
Yeah.
All the
In times down.
Well, you can just mention,
no, it's standard model calculations. Okay, just extrapolate it up to our energies. Whether that extrapolation is done right or not, of course, is subject to debate. Okay, so we take the standard model as we understand it at current experiments, put it into a big simulation program, and then crank the energy up and see what comes out.
Actually, I think I missed that what was above B quarks. So if it was lighter quarks, then it is understandable.
Top quark.
Above was top quark production. So B quarks is many orders of magnitude bigger than top quark
that makes
production.
sense.
But top quark production is still pretty significant.
But you are not talking about S and C quarks.
No, there's so many of those that you can't comprehend it.
Yeah, that's what I...
Yeah.
Yeah, okay.
No, so we're making BB bar, and then you add several orders of magnitude to get J size.
Yeah.
Okay? We're just...
Yeah, that is... what
Every collision we must be making J
yes,
size.
I cannot be able to...
Yeah. That's the problem we're fighting in doing the analyses, is there's huge, look at this. We've got, 100 billion BB bar events for every 200 Gluino events. Okay? So the whole game is to take data at 40 megahertz, at 40 terabytes a second, filter through it as quickly as you can to knock it down to a few terabytes a day, all in the hope of picking out that handful of events. That's actually a fun intellectual challenge. I like working on that.
Small needle and large haystack.
It's a really tiny needle in a big, big haystack. Yeah.
This whole project is based upon individual particles in a way. But what happens when everything comes together as an interaction? And I tend to think of molecules and atoms, where you're transferring
There's
from
a whole
quantum to classical physics.
There's a whole other research program here that I haven't even talked about. And one of the things they'll do with the LHC is what's called heavy ion physics. We actually will take like gold nuclei and run them into each other. And that's another epoch in the evolution of the universe, where presumably in the early universe there's a quark gluon plasma that existed as a phase of the universe, and then it was out of that the atoms in that formed. And so there's a whole research program to study the quark gluon plasma by running nuclei into each other. That isn't what I do, but we'll do it with our detector. And I have colleagues at Rice who worry about that. Yeah. So there's all these different epochs that have to be studied in the early universe. And I'm just an ultimate reductionist, so I want to go for the smallest, highest energy thing, and that's me. And there are other people who fall into other areas. So the physics I talk about is biased by what I'm interested in.
My name is Alex Monchak. I'm taking this course as a continuation education student, and the course is about publishing. So I was wondering, could you talk a little bit about publishing and what journal, and then the method part of the journal publication, your experience with reproducibility from what you've read, and then since you're from Rice, I was wondering if there are university presses at Harvard and Princeton. Do we have one in Texas? And finally, since it's at Rice, there's a Baker Institute that just came out with the report for space. I was wondering what's the thought of the relationship there?
Well, the person who came out with the report about NASA now is Neil Lane, who is somebody I know quite well and has an office down the hall from me. So we talk on these things. And he's actually on the board of overseers of Fermilab. And I think there's the Gathering Storm report. There was this report done by people from industry, Congress, science, that said we have to double our investment in science. And that's all sciences across the board, including fundamental science, what I do, what NASA does, and things. And it's, both parties in Congress say they support that goal. Obama says he supports that goal. They took science spending out of the stimulus package. So, there are things I don't understand. The publication process is interesting because what happens in these big collaborations is there's actually a very rigorous scrutiny that goes on within the collaboration. So there will be assigned a team of scientists to go through a proposed publication in excruciating detail, even more detail than you would get in a PhD thesis next examination. And we can call on, say, prove this, prove that, show us your notes on this and that. And so there's a whole vetting process that goes on within the collaboration before any result is allowed to go out in the world. So for example, I am only allowed to show you plots like these that have gone through such a process. Okay? So this is like an official statement from the collaboration that's gone through an informal review process. Once you go through that process, you then submit it to the journal and they go out to referees and you go through the process again with the referees. The external referees aren't part of your experiment, so they don't know all the little nuanced details of how things could go wrong. Okay? But they can still... I certainly reviewed a paper a few weeks ago that was 70 pages long, and they got 30 pages of somewhat critical remarks back from me. They have a lot of work to do. I suppose they went through that. There's a little bit of a shift. The LHC experiments are saying that they want to publish in freely available online journals. So, rather than in journals to charge huge subscription fees to the universities, it's more easily accessible. We'll see what happens. In the US, we've tended to want to publish in physical review letters and physical review. And the equivalent in Europe is Physics Letters B, but the LHC experiments at the moment are committed to online publication. Certainly what happens now is every paper that's coming out, you can go to public archives and download. Although when you do that, they haven't been refereed yet. So change is in the air there. Yep.
Since it appeared so often on your charts, what's a femto barn?
Well, thank you for asking, because
Had to ask.
yep, look at that. What's a femtobarn? And if I click on it, I go to what a femtobarn is. Okay, so this is a common particle physics unit. A barn is a unit of area. So if you're going to calculate the probability of hitting something,
It's cross-section.
it's cross-sectional area is a good thing. And a barn actually comes out of Los Alamos. This actually the size of a uranium nucleus, what defines a barn. And the name is a joke, you know, they were trying to shoot neutrons at the uranium nucleus at Los Alamos, and you couldn't hit the side of a barn, because that's what the name came. Okay? So I think, okay? So that's 10 to the minus 24 centimeters squared.
Oh, yes.
A femtobarn is 10 to the minus 15 of those. So we're talking about really small things. So 10 to the minus 39 centimeters squared. So that's the cross section. So there's the barn. Okay? And then we use inverse barns as a way of measuring how much beam we've collided. And that way we can take the cross section for the process we're measuring and multiply it by the luminosity in inverse barns, multiplied by our detection efficiency, and that'll tell us how many events. Okay, so we will do 20 inverse femtobarns in the early running, although the first year running is 200 inverse picobarns, which is a factor of 1,000, or a factor of 100 less than this. Okay, but ultimately we'll be doing 200 inverse femtobarns a year. And then we're already working on the super LHC and the luminosity upgrade. Okay, so we use these really bizarre units because they're convenient.
They're SI, right?
I don't know. They're nuclear and particle physics units.
Okay, any other questions? All right, let's thank our speaker. Also, we made an announcement last Thursday's talk that we're having a new Facebook page for the UHCO physics program, and that'll have information about some of the talks that we're doing or any upcoming events. So if you can just go there and just sign up for it. And we're going to be eventually moving towards that as a way of distributing information as opposed to sending it out through the email list. And the nice thing about it is that you'll be able to subscribe or unsubscribe, and you don't have to worry about getting anything you don't want.
Can you talk about the Facebook? UICL Facebook?
Yeah,
Did you mention it already?
yeah, that's what I was just saying.
No, I mean, everybody is like, they can come and just join it.
Yeah. 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 Yeah.